we're going to first look at f of x equals 1 over x minus 2. With any luck, you should all be able to tell me very quickly and very easily that this has a vertical asymptote at what value?
X equals 2.
X equals 2, right? Because the denominator would be 0 if x was 2, but the numerator would not be 0, right? If they both become 0, then that gives us a whole. But since just the denominator is equal to 0 and x is 2, it gives us a vertical asymptote. And whenever we look at a function as it approaches its vertical asymptote, we know that that function is going to either decrease very rapidly or increase very rapidly as it goes towards that asymptote. And the technical term we use for getting very steep or increasing very rapidly is that it increases or decreases without bound. And what that means is that it goes up so quickly that it never is successfully able to make it over to that next whole number of x equals 2 or whatever that asymptote is at. And so if we were to try to investigate a limit as we approached, let's say, 2 from the right-hand side of this function, we're not going to be able to obtain a real number value from it because it's not getting close to, let's say, 1 million. 1 million's a big number, right? It's not getting close to 1 million because at some point it passes through 1 million and gets higher than that. And it's not approaching 100 million because eventually it gets to 100 million as it goes up there and surpasses it, right? And no matter what y value we might guess that it's approaching, that's always going to surpass that as it approaches that asymptote and still continue up more and more and more. And so we would say that as x approaches 2 from the right-hand side, so just the right-hand limit, we're going up and up and up, we'll say that limit is infinity. And if we approach 2 from the left, we might say that since it's going down and decreasing without bound, that limit ought to be negative infinity. Okay? Everybody good with us calling those limits infinity and negative infinity?
Yep.
All right, perfect. So the problem with that, though, is that a limit for it to technically exist has to approach a real number, and infinity is not a real number, and neither is negative infinity. Neither of them are real numbers. So technically, anytime we state that a limit equals infinity or negative infinity, that limit really doesn't actually exist. So if this was an AP multiple choice section on your calc test this year, and it asked you, what's the limit as x approaches 2 from the right of f of x, and if it was multiple choice, they might put out an answer of infinity, or they might put out an answer of does not exist. Both of those answers would be correct. They wouldn't put both of those answers on the test. They would only put one or the other. But just be aware that they might label it as infinity or negative infinity from the left, but they might also say that that limit doesn't exist because infinite limits don't technically exist. Everybody good with that?
So the two-sided limit also wouldn't exist?
Yeah, so for this one, the two-sided limit definitely doesn't exist because from the left it's approaching negative infinity and from the right it's approaching positive infinity. But there are some functions, and we'll look at some on the next page, where they're both approaching infinity. And for those ones, we could say that the two-sided limit is infinity, even though still technically that one wouldn't exist either. Everybody good there?
Yep.
All right. So really, these are the 3 different sort of options of what we could look at if both sides of our function are approaching the vertical asymptote. They could both be going up towards infinity, where the limit from the left is infinity and the limit from the right is infinity, and the two-sided limit is also infinity. Or it could be negative infinity from both sides and the two-sided limit is negative infinity. Or it could be negative infinity from one side and infinity from the other, where the two-sided limit, we can only say that it does not exist. But we will always remember that no matter what, none of these limits, the limits as x approaches -1 from the left and right, and the limit as x approaches 3 from the left and the right, and 2 from the left and the right, none of these limits actually exist. We just use infinity and negative infinity to help guide us if we want to know what the function is doing and how it behaves. Good? So let us, without graphing this function, see if we can find the one-sided limits and the two-sided limit at the vertical asymptote. What's the vertical asymptote? That's the first thing we should probably figure out, right?
4. X equals 4.
Vertical asymptote ought to be x equals 4. So what we're looking here for is a limit as x approaches 4. We want to do from the left or from the right first. I'll leave it up to whoever says first. Or no.
Let's start from the left. How about?
From the left. All right. Let's start from the left of f of x. So now this is going to be super technical. Not really. In fact, it's going to be as far from technical as we can get in a calculus class. What's a number that's close to 4 on the left-hand side of 4?
3.
3. All right, that's good. That was what the first thing somebody said in fourth period today, or whatever, period 1, period 4, whatever they call it. Yeah, 3. 3 is close to 4 from the left, right? Sure, closer than 2, but it's not that close, is it? Is there a number that's closer to 4 from the left?
3.999.
3.999. That's certainly closer than 3 is, right? I mean, 0.999 closer. But that's not very close either. How about we use something like 3.9999999999999999999999999999999999999. Sound good? Everybody good with that?
Yeah.
Yes.
Yeah. All right. Well, if x is that number that I just said that I'm not going to say again, the numerator is still just 1, right? But what about the denominator? What's 3 point all of that, all those 9s minus 4? Well, it's a very, 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 very small negative number, isn't it? It's 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000001 ish. I don't know. Maybe I didn't quite say the right number of them, but true. It's a very small negative number.
Yeah.
Okay. And then we have to cube it. What happens if we take a very small number, a number that's between 0 and, well, number that's absolute values between 0 and 1, and cube it? What happens to that number when you cube something?
It gets a lot smaller.
It gets even smaller. And in this case, since it was negative and we cubed it, it should stay as a negative. And we'll say it's an even smaller negative. It doesn't matter if it's even smaller though. What happens when you take 1 and you divide it by a very, very, very small number?
Get a very, very big number.
You get a very, very, very big number. And in this case, a very, very, very big negative number. We get negative infinity. So that if we graphed 1 over x minus 4 to the third and looked at what was happening as x approached 4 from the left, it should be dropping down towards a vertical asymptote. Everybody good with that?
Yep.
All right. And what about the limit as x approaches 4 from the right? 1 is still 1, right? Well, if I put in 4.00000000000000000 blah 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 000 blah 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 001, right? And I subtract the 4 from it, I get a very, very small
Positive.
right? And if I cube that, that small positive stays positive and becomes even smaller. And what's 1 divided by a very small positive? It becomes a very large positive number. Good or no?
Good.
And so the limit as x approaches 4 of f of x cannot possibly exist because these had different values. And technically, none of these 3 limits actually exist, right? We just like to pretend that they do. And just for the sake of making sure we haven't lost our minds completely, not completely, only partially, at least maybe, 1 over x minus 4 to the 3rd power. If we look at x equals 4 as we approach from the left, what's it doing? It's dropping down to that vertical asymptote. And as we approach 4 from the right, it is increasing up to positive infinity. So from the left, negative infinity, from the right, positive infinity. Everybody good there?
Yeah.
Cool. All right, let's do another one. We'll do this one a little more quickly than the last one. 1 over x minus 2 squared. What's the vertical asymptote?
X equals 2.
Equals 2. So we want to limit as x approaches 2 from the left of that. We want a limit as x approaches 2 from the right of that. And we want a limit as x approaches 2 of that. From the left-hand side, that's something like 1.9999999, which gives us a very small negative inside those parentheses, right? But when we square it, it becomes a very small positive, making this infinity. And what about from the right? Inside the parentheses, we have a very small positive, which when we square it becomes an even smaller positive and we get infinity. And we could say this one is also infinity, even though technically none of these exist. Everybody good with that or no? There it is, 1 over x minus 2 squared, both sides. We're approaching that asymptote of x equals 2 and going up towards infinity. Any issues with that?
Nope.
All right. We'll do one more of these before we move on. This one is a little different. First off, it's not just a constant in the numerator. And it's also not something squared in the denominator. What do you think the first thing we need to do to find the limits at the vertical asymptotes is?
Factor.
Factor that denominator so we can figure out what those vertical asymptotes are, right? 4x over, what is this factor to? X and x, right? And looks like minus 1 and minus 3. Everybody agree with that?
Yep.
Cool. So, you guys want to do the asymptote at x equals 1 first or at x equals 3?
X equals 1.
All right. Limit as x approaches 1 from the left, we'll say. So if x is approaching 1, what is 4x going to be about?
4.
Should be very close to 4, right? It's going to be just under 4, but 4 is good enough. 1 from the left makes this a very small negative. And then 1 minus 3 gives us negative 2. So the negatives will end up canceling. And we have 4 divided by a very small positive down here, which should be infinity. And if we do this from the right-hand side, this ought to be 4 in the numerator, but a small positive times that negative 2, which ought to give us negative infinity. Everybody good with that or no?
Yeah.
And so we would say the limit as x approaches 1 of f of x doesn't exist. And what about for x approaching 3 from the left? What should that give us? this. We should put a 12 up there in our numerator. And then a 2, and then a small negative. So that should be negative infinity. And as we approach 3 from the right, we should have 12, and we should have 2 times a small positive, which ought to give us positive infinity. And this limit as x approaches 3 also does not exist. I don't know why I forgot to write my f of x's in there for each of those. But. And we could confirm this if we wanted to, just by looking at our graph real quickly. So 4x, and what was it? X squared minus 4x plus 3. Is that right?
Yeah.
Cool. So as we were approaching 1 from the left, what did we say? We said it should have been infinity, hopefully, right? Yep. And as we approach 1 from the right, it should have been negative infinity, which we can see in this piece down here. And as we approach 3 from the left, that'd be this piece over here, it should be negative infinity. But as we approach 3 from the right, it should have been positive. Everybody good with that or no?
Yep. Good.
All right. Off to a good start. You guys don't mind going like 30 or 40 minutes over just to make up for that quiz, right? Let's get through all the rest of these notes.
A little bit.
Yeah, it's just a little bit. I agree. It's just a little bit over. Not a big deal. All right. My 7-year-old, I think, just shouted from the other room that I shouldn't go 30 or 40 minutes over. Don't worry, I'm not going to. All right. That's it for vertical asymptotes. Now we're going to look at what happens as x approaches infinity, or maybe also when x approaches negative infinity. So if I put in a very large value for x into this, and that's supposed to, it's really hard to see with a fraction bar on that. Maybe you can see it. That's 2 plus 1 over x. What happens if I put in a really big number for x?
It becomes a really small number.
Right, this 1 over x piece, this should go towards 0, right? And 2, if x gets very large, is just 2. So one would think that if I put in very large values for x here, as I look towards x approaching infinity, my function should be getting closer and closer and closer to a y value of 2. And graphically, what do we call that?
Horizontal asymptote.
Yeah, we call this a horizontal asymptote, and it should be for y equals 2. So let's just, because Desmos is here and so convenient, there's 2 plus 1 over x. And you'll note that it sure does look like, if I throw in that y equals 2 value, sure looks like there's a horizontal asymptote of y equals 2 running through there between those two different pieces of it. Would you guys agree?
Yeah.
Yes.
Okay. All right. So anytime you are asked to verify or prove that a function has a horizontal asymptote, you need to look for a limit as x approaches infinity. Now, that's not the only thing you need to do, but that's what we're going to start with. You've got to look for the limit as x approaches infinity. And since that's what we were doing here, that told us our horizontal asymptote. Hopefully, in the last couple of years, one of your teachers taught you a bunch of rules for finding horizontal asymptotes with rational functions, right? A polynomial over a polynomial, something like 2x squared minus 5 over 3x squared plus x plus 2. Did one of your teachers teach you some rules for that? if you don't remember all those rules, it's okay. But did they at least teach you them?
Yeah.
Yeah,
Okay. All right. See, I know you all are afraid if you say yes, I'm gonna be like, all right, name all the rules, and then you're gonna sit there and be like, I don't remember any of the rules. Right? That's okay. We're gonna learn the rules all right now in the next 9 minutes. And you're going to, at least if you don't remember the rules, know how to come about those rules on your own. So here we have 2x squared minus 5 over 3x squared plus x plus 2. Looking for a horizontal asymptote, we should be looking at a limit as x approaches infinity. So the way we're going to do this for any rational function is find the highest degree. So first off, what's the highest degree of any term in this rational function?
two.
Right, the highest degree is 2. So we are going to divide everything. We're going to divide every term by x squared, by the simplest polynomial we can come up with that has a degree of 2. So that's what I've done here. I've written the limit as x approaches infinity of all that original junk that we had, but all divided by x squared. And there's nothing wrong with that, right? Because if you wanted to like try to simplify this down, you'd take the reciprocal of the denominator and multiply, and then what would happen to those x squareds? They would just poof, cancel away, right? Yes, that's what they would do. Okay, so we're going to divide everything by x squared. So that gives us a limit as x approaches infinity. What's 2x squared over x squared?
2.
2, and then minus 5 over x squared. And then what's 3x squared over x squared? That's 3. X over x squared. And 2 over x squared. Everybody good with that so far? Okay. So as x gets very, very large, as x goes towards infinity, what's 2? This is an easy question.
Isn't it just 2?
It's just 2. Yeah, I mean, it doesn't matter what happens, 2 is still 2. A constant is just a constant. But what about as x goes towards infinity? What happens to this minus 5 over x squared?
Super small.
It gets very, very tiny, right? It gets very, very close to 0. And 3, as x goes towards infinity, is just 3. But what about 1 over x and 2 over x squared? As x goes towards infinity, both of those also become
0.
0. And this is your first rule that you should have learned at some point in the past, that if you have a rational function and the degrees of the numerator and denominator are the same, you divide the leading coefficients and it gives you your answer. Well, the reason why that works is because you can divide everything by that highest power, and everything but the constants in the front of these leading, everything but those leading coefficients will cancel out and become 0, and you'll just be left with the quotient of the leading coefficients. Does that make sense?
Yes.
Yeah, that's where that rule came from. Isn't that exciting? It's like you're learning how math works and why your old teachers just told you this is a thing that works and don't question it, it just works. Well, this is why. Ooh, exciting. Any questions on that?
Nope.
All right. Let's do another one. 2x squared minus 5 over 3x to the 4th plus x plus 2. So what is the highest degree?
4.
4, right? We're going to divide everything by x to the 4th. So we're going to be looking at a limit as x approaches infinity of 2x squared minus 5 over x to the 4th over 3x to the fourth plus x plus 2 over x to the fourth. Good or no? Hopefully okay. All right, what about this numerator up here? 2x squared over x to the fourth ought to be 2 over x squared minus 5 over x to the fourth. And down here, we ought to get 3 plus 1 over x cubed plus 2 over x to the fourth. Everybody good with that? What happens to both of these terms?
They get really close to 0.
They get very close to 0. And what happens to both of these terms? They also get very close to 0. We just end up with 0 over a constant, a non-zero constant, so we get 0. And the rule that you should have learned way back when was that if you have a rational function and the degree of the numerator is less than the degree of the denominator, you should end up with y equals 0 as your horizontal asymptote. And the reasoning being, everything in the numerator will come out to be 0, whereas you'll still have a non-zero constant in the denominator. Good or no? All right, one last one, because there was 3 rules for these rational functions and their horizontal asymptotes. This is the one where the degree of the numerator is more than the degree of the denominator. What do you think we should divide everything by?
X cubed.
X cubed. So we're going to get a limit as x approaches infinity of 2x cubed minus 5 over x cubed and 3x squared plus x plus 2 over x cubed. Giving us what in the numerator? 2 minus 5 over x cubed. And in the denominator, 3 over x plus 1 over x squared plus 2 over x cubed. And this time it looks like everything except that 2 ought to go to 0. So we get 2 over 0, which is undefined. And that tells us that there is no horizontal asymptote. And that was the rule you should have learned way back when, for when the degree of the numerator is more than the degree of the denominator in a rational function, that you end up with no horizontal asymptote. And now you know why it's true. Isn't that exciting? Any questions on that?
Nope.
Cool.